Thanks for the organizer for letting me talking, and also for the audience who is still here after yesterday evening. So today I want to talk about the Euler mass function in clustering dark energy models. I'm not trying to use it to solve the sigmoid tension or the S3 tension or variational tensions. So that's not the purpose of this talk. But I would like to show you that the Euler mass function is a great tool for cosmology, but at the same time you have to be very careful when you use it, especially if you go using it for models beyond the standard ones. And when I say standard models, I don't only mean the lambda CDM model, which is more or less understood, let's say that, but also models where dark energy, whatever is its equation of state, is only modifying the background, so where we don't consider any perturbations. Okay, so as we were seeing in these 3 days of conference, we have two sets of observables. We have this late and early times, but early times they are pretty nice because it's based on the CMB, it's linear physics, so we can do all calculations, let's say, by hand, and we understand very well the physics behind. Thanks to this, we also have very precise codes, this Boltzmann code, which predict the matter power spectrum and the CMB spectra, and we can also have precise measurements. At the same time, we can also use late times observables, which are based, for example, on the matter power spectrum, which in this case is non-linear, so there are complications because of nonlinearities, and clusters and galaxy clusters, where here the nonlinear physics is really highlighted, but besides that we also have to take into account baryonic effects, and this introduces many uncertainties. In fact, normally for this kind of studies, we do not really rely on analytical methods, but on numerical methods like n-body simulations. And if you are familiar with n-body simulations, you know how complicated it is to actually converge to a result. Because if I write a code and you write a code, probably the two codes give the same result up to a scale which is either linear or quasi-linear, but if you want to go to non-linear scales like k of the order of 10 inverse megaparsec, you have to put really a lot of effort on that. Not to mention that if you want to do it analytically, it's very complicated. So I'm not going to spend time on the CMB because we already talked about this also this morning. So I will concentrate on cosmology for clusters. So you know that clusters are the largest gravitational bounded objects in the universe. We are very sensitive to the cosmology, especially in the high mass state. So the more massive is the halo, the more sensitive is to the cosmology. The abundance has a strong dependence on the matter density and the normalization of the matter power spectrum, and we will see how this enters into theoretical formulations. And you can observe them in different bands. And this means that you can get information from multi-wave analysis, but also you can get the mass from different observations, and then you can check whether the mass that you obtain from different wavelengths is the same, and usually that's not. And therefore there is a bias that you have to eventually calibrate with simulations, in particular with hydrodynamical simulations, which are even more complicated with standard n-body simulations, to get the mass right. Why this is very important? Because as we were seeing with the talk of Jenny on Monday, if we want to describe halos, we have to use the halo mass function. But as the name says, it heavily relies on the mass. And if you mismatch the mass, then you are going to get completely different results with what you actually should get. And this is the zero level complication. And we will see that when you talk about masses in models where dark energy is clustered, which is the topic of this talk, then at the moment we have really no idea what's going on there. So we only have ideas of how things should be, but we would like to test them. And because of this, so getting the mass is tricky because, for example, you have to go from an X-ray measurement, and therefore you need to use scaling relations, which eventually are based assuming that your cluster has spherical symmetry. That's not true in general, so this already introduces some problems, and then we get additional complications. So we saw that there are many tensions. I will rely on the sigma 8, and we saw that there is a discrepancy between the Planck and the set number counts, and this transfer in counting the halos for very massive objects to a factor of 2. Okay, so to solve the sigma tension, there are really different solutions. You can see some of them. And if you go to late times, usually you want to try to modify gravity. Also because, as Emmanuel was showing his very nice talk this morning, what you would like to do is eventually to have less strong gravity, and therefore you modify your gravitational constant, making it smaller than 1. Or let's say G effective over G is smaller than 1. And one of the proposed solutions for doing this is the clustering dark energy. And in particular, we will see that you can achieve this if we have phantom dark energy, so when W is smaller than -1. So what is the Euler mass function? Probably you are all familiar with it, but just to make a short summary, this just represents the number of halos per unit mass and volume at a given time. So if you want to calculate it from a theoretical point of view, it's relatively easy to do that. You can show, and we will see that it's very sensitive to cosmology in the high mass state, but even theoretically, getting it right is not that easy. And what you usually do is say, well, baryons are a few with respect to all dark matter. They don't exist in the universe, so if they exist, they behave just like dark matter. Of course, that's not really true when you do a proper non-linear analysis. Then there is a transfer of power from the outskirts of halos to the internal part, and therefore also where the mass determination becomes different. Now, the problem is also that you want to compare your Euler mass function from a theoretical point of view or from a numerical point of view with observations. But because of this term here, the volume, you need to know in advance how big is the volume that you are spending. So you want to convert redshift to a distance, and you need to assume already a cosmological model. So this means that you cannot really use an observed Euler mass function to do your analysis, because that already assumes a cosmology. So you might want to try your fancy or whatever cosmological model with something which is already been calibrated with a lambda CDM model. And therefore, usually you would like to go to local measurements, so where halos are pretty close to you, and where when you can just neglect the cosmological evolution. Okay, so how is theoretically defined the mass function? Is this formula here. Doesn't matter what all the term means. The only important part is this. You see, it's the new term, which is just this function delta c, which is a function of time. In reality, it's almost constant. It doesn't really change with time. For the Einstein de-Sitter, this famous 1.686 values. This is the growth factor, and this is the sigma 8 at redshift 0. Then there are these two parameters, P and Q, which have been determined via fits to encode the simulations. But then, of course, this is just a theoretical mass. You want an observational mass, and how you go from the observed one. So how you get the observed one, you need to go, for example, as I was saying, by scaling relations, and you see, for example, it's proportional to the X-ray temperatures. But then there are correction factors, which depends on the realization of your objects, which, from a theoretical point of view, is already not really well understood for a lambda CDM model. So already for this, you are introducing a lot of uncertainties purely at the theoretical level. So what are the solutions that people were proposing, just taking the Euler mass function and playing with it? So you assume a lambda CDM model, and you say, well, whatever mass function that I take, as the one that I was showing, is a kind of fit. So I can keep my parameters free, and I adjust them such that I go closer to sigma 8 to the lambda CDM model. Sorry, to the sigma 8 value from Planck. And you can see that in reality that's yes and no. If you do that for kids, so if you use the original formulation, you are here. If you just then change these two parameters to the slope, you actually get a smaller values. So then you get even farther away. While, for example, for death, this works much better. Whether you believe this or not is another matter, but it's just a way for showing that these analytical formulations have huge uncertainties. So you can just play with them. And why is this? Because these parameters here, like the P, and there should be a Q somewhere, which now I don't see. But it's okay, there should be another parameter which I don't see. They just rely on the accuracy of your simulations. The bigger is the simulations, the better resolved are your halos, and the better these parameters can be found. Recently, so 3 years ago, there was another paper where actually it was shown that if you use a more advanced Euler mass function, halos at redshift 0 will predict a sigma 8 of the order 0.81. So very much in agreement with the lambda CDM model. Also this one, so might just indicate there is a problem in calibrating your mass function, and therefore eventually just the mass of your halos. So perhaps that's the main ingredient that we don't get right. But if we go back to some more exotic models, as I was saying, with clustering and dark energy, so this is one of the solutions proposed for the sigma tensions. So what's clustering dark energy is just your standard dark energy model where you introduce perturbations. Now, if you want to make it cluster, you need to assume that its sound speed is small, because if it's 1, then it's just smooth. It's not going to cluster on the scales that you are interested in. So you assume that the sound speed is 0, so delta P over delta rho is 0, and then you can show that the dark energy perturbation, at least in linear regimes, are directly proportional to the matter perturbations. But the interesting part is this term, 1 plus W. Why? Because if you have a W which is bigger than -1, delta M is positive, delta dark energy is positive, so you get a nasty clustering. If W is smaller than -1, then for a halo in matter you get a void in dark energy, and vice versa. And this means that in this case, since they are proportional, if this gets big, this can get big in absolute value, and therefore the dark energy perturbations contribute substantially to the whole overall budget in perturbations. And therefore you can define a new perturbed quantity, which is just the average sum of the perturbations. This is not always done. We don't know if it's correct to doing that, but from a physical point of view it makes sense, because if you replace dark energy with baryons, of course, you can then combine together and get the standard growth factor equations, for example. So at least in this formulation it makes sense. It might not be entirely correct, but it makes sense physically. So how do we solve these equations? To study the perturbation, we consider a fluid approximation. So on small scales, here there is no scale dependence, and just get a continuity equation and an Euler equation, which are standard one, except for the terms due to the equation stated at the ground, and then you modify the Poisson equation, adding one additional term, this omega dark energy, delta dark energy. If you just think that to this, to rewrite as the standard Poisson equation, you can factorize omega dark energy, omega matter, delta matter, and then this 1 plus delta dark energy over delta matter, besides prefactors, this will be your new gravitational effective gravitational constant. And you see that if delta dark energy is negative, then you're going below 1. If it's positive, you're going above 1. Oh, okay. So now how this enters into the mass function? You solve these equations assuming the collapse at a given time. For simplicity, you can assume 0. So you solve these equations, you get the initial overdensity such that your structure collapses today, or at the ratio that you want. You get, when you solve the linearization part of these equations, you go back to this one of your favorite halo mass function. You plug the numbers here inside your growth factor, which you calculate, and then you can get your halo mass function. Now, according to what you do, using exactly the same formula, you will see that you get completely different results. So this is the standard results that you get when dark energy is moved. So it only changes the background and therefore the volumes effects. So because W is smaller than -1, you get more halos just because your volume gets smaller. Instead, if you are in a phantom regime, you get less objects because with respect to the lambdas again, because you have volume effect, which is larger. Now, suppose that dark energy is clustering. Now you see that you get a completely different result. And what did I do here? I just said that my Poisson equation is modified in this way. But what we were saying a few minutes before is that if you have perturbations in dark energy, then you are also going to have either voids or dark energy mass. What does this imply? That how you define the mass of a halo in this case is just the dark matter mass is dark matter plus dark energy, but for dark energy, which one it is? Because dark energy contains pressure. So it's just the delta rho or the delta rho plus 3 delta P, something like that. We have no idea. So we can speculate which one you want from a generality's point of view. It should be delta rho plus 3 delta P, but might not be the case. We really don't know. So when you do that, Now you have to take into account the new mass. In reality, mass is not equal to rho, should be just proportional to rho. But what happens here is that normally you assume that the total mass is proportional to delta m, so delta mass of the matter component plus the mass of the perturbation of the dark energy. Why is that? Because we rely for these things on an embodied simulation. If you have an embodied simulation with a cosmological constant, lambda doesn't enter your mass definition. Therefore, so I messed it up. So if here I put rho dark energy, which is rho background plus delta dark energy, then I am in disagreement with a standard simulation where the cosmological constant is there all the time. That's why we just use this part here. So if the mass changes, you need to correct either the mass or the mass of the halo mass functions, because these were not tested for this kind of models. So you can have two different proposals. One is you just change the mass. You basically escape as taking into account the contribution. And you see, once again, we behave the same way, but in the opposite way as before. So now, instead of making more objects, you get less objects. Or you can make something more sophisticated, as Creminelli and collaborators were doing 13 years ago, is that you not only change the mass, but you say, I don't trust my halo mass function anymore. Therefore, I make a correction which is proportional to the ratio between the mass function when I consider collapse, when I consider the perturbations, over the mass function where there are no perturbations. They try to justify this, but it's just a proposal as anything else. There is no real fundamental physics behind this assumption. And now what happens, you see that while for me we will be having the same way, now you get that for phantom models, you get more objects than for standard quintessence models. The interesting part for is this one, that you see for CS, in reality this should be CS squared equal to 1, you get more deviations than when CS squared is equal to 0. Now, CS squared equal 1 just means at all effects smooth dark energy. Equal to 0 means fully clustering dark energy. And why fully clustering? Because the sound speed of matter is 0. And now you see a funny thing, which for us is bad, because you get closer to the lambda CDM predictions. So if the dark energy is clustering, your model, instead of behaving more differently from the dark energy component, from the lambda CDM model, becomes more similar. And this is independent, or at least we tried several models, actually a lot of models, changing the W also as a function of time. It's always the same results, independently of W. And why is that? Because changing W changes the evolution of the matter, but at the same time, you change the total perturbations. And somehow the two effects partially cancel, and you get closer to the lambda CDM model. Okay, so you see, you can use the halo mass function, but you have to be very, very careful of what you are doing, because all this has not been tested with embodied simulations and even less with observations, just pure speculations. And you see that you can get different results. And of course, if you get different results, your conclusion will also be different. In particular, your mass function is fair because you derive in a certain regime, and then you can insert something which might be plausible but wrong, and you get the wrong answer. Now, just one more minute, is that everything? No. Even at the lambda CDM level, we have theoretical uncertainties at very fundamental level, because all these calculations were assuming that your halos are very isolated, not socializing with the others, and not rotating. So we are just like this all the time. Now, you can do something more elaborate and say that they more or less socialize, so we are not spherical, but we become ellipsoidal and start and rotate, because we know what they do. And in this case, you can construct two halo mass functions, just changing the values of the parameters, and then fitting one to the other. And you get about 1% error in the determination of sigma 8. So if you start your fiducial model 0.3 omega matter in 0.8 in sigma 8, then you get something which is around 1% off, which might not be too much, but then this always propagate, because from a halo mass function you can get via the halo model your matter, nonlinear matter power spectrum. And the same, actually it's even worse, if you start with the equation of state, which is exactly -1, and when you see that you go preferentially towards the phantom regime, but not by a few, but actually by quite a lot. So you have to be careful already at this level which models you are fitting to. Okay, plus then 2 days ago there was this paper saying that probably all of this is useless because we are getting close to each other, so perhaps none of this will be necessary anymore. But if you have to remember something from this talk, is that value mass function is a great tool, but please be careful because you can put something plausible, which is wrong, you get something which might be plausible, but is completely wrong, because this is all nonlinear physics. And thanks for your attention. Yes.
So in clustering divergences, the sum of each square can be between 0 and 1.
Yes.
So this is an independent input in your
Yes.
equation. So what are you assuming for that?
I'm assuming 0 because it's where I get the strongest effects. Now, in principle, you could take whatever value between 0 and 1. If you put 1, then it's equivalent to smooth model. Perturbations are so small that the difference are just in 2
So you are considering the strongest case.
The strongest case. But you see, they are not so big. Of course, whether the value is exactly 0 or not, it will be at the fundamental level, so you should go by a Lagrangian. Then whether it's, so then you should go for these K-essence models. But then you need to write it down. At this level, just pure phenomenology, just because it's much simpler to deal with a W rather than with a potential or whatever is your Lagrangian.
Could you try to look at the turnaround radius? What's happening? You know, you understand this is 2.6 of the Euler radius roughly. Did you get scattering on this?
So that's a good question. It depends on your equation of state. So now I don't remember how it happens for this, but it's a function of your equation of state. You can get closer to lambda CDM if W is very negative, because when the effect of cosmological constant is important very, very late, so practically for z equals 0. If you get something quintessence going towards curvature, so -1/3, you get more far away. But the exact value depends on W. And of course, it also depends at which time you come to the mass function, because that depends on time.
Just two short questions.
Yes.
One is your analysis change abruptly if you are considering field galaxies or cluster galaxies.
No, I don't think it does. I don't see why it should change abruptly.
Because the field galaxies are not evolving, while the galaxies inside the cluster are going to evolve. So it could be a mismatch considering the...
That could also be, but at the end this kind of thing is kind of static because you fix your time. So I'm not really sure that that's really matter. I should think more about it. I never thought, so I don't know.
Because the amount of dark matter inside a cluster...
Yeah, it's different. But they are more or less average quantities, so perhaps they are compensated at the end. But then who knows?
Another question?
I was wondering, in the lambda prediction of the mass function, is it accounted for somehow that, I mean, if you have a halo, you expect it to be close to other halos, I mean, so that it's living in an environment that's not seeing the background density, but it's seeing it?
Yes, so that's a very good question. Lambda CM doesn't care for that. That's important if you are considering modified gravity, like for example F/R models, then the environment becomes really important. And that's because when you have screening mechanism, and then of course it can be totally screened, unscreened, partially screened, and therefore there is an equation which takes into account the environment. For the lambda CM, this doesn't happen. Now the whole purpose of all this is that a few months ago there was a paper by the group of Stefano Corasaniti in France, saying we are going to run n-body simulations for clustering dark energy in the fluid approximations. And this means that finally everything that I was showing now can be really tested and compared. perhaps some of this is correct, perhaps at the end everything is wrong and we have to go a few steps back and rethink everything. But also because in a MOD simulation, it will depend how we do that, and therefore it will be how you define the mass. And then you might wonder also why I was, you see, where are they? So here we use Tinker, and here I just use Chet and Thorman, which is older. And that's because I want to stay on the safe side. The Tinker mass function or Morrison mass function, they have all the three parameters that rely on the overdensity, on the virial overdensity of your clusters. That is, you observe it, that's easy. Theoretically, we don't know how the realization works for the lambda CM, and even less for whatever other model. And this means that you have a lot of uncertainties. And therefore, it just explodes in terms of things that we don't know. So in principle, you could do the same things with the present shatter. You get the same results, qualitatively, just the difference is changed in amplitude, but it's the same result.
Okay, any other question? Yes, please.
Go to the next slide.
This one?
Yeah, I didn't understand what point we were making about it.
So we were making that there is a sigma 8 tensor just because we don't know accurately enough the functional form of L mass function. So we say, so your L mass function should do something like this. This is the low mass, this is the high mass regime. And now just do like this. Change the tilt. And according, so if you can just change the exponent or some other parameters of the mass function, if you change this and you do a fit, you get a different sigma 8. Sometimes you get something closer to Planck, sometimes you get something more far away. That's what we do.
You said something about with kids it doesn't work, it does it works or something?
So, if I interpret this correctly, so this is this one here. So the standard Chet and Thorman is here. If you make it more tilted, you get a higher sigma 8, so you go closer to the Planck value.
Yeah.
While for kids, you get exactly the opposite, but they don't say why. At least I couldn't find a real explanation. So this is the or I mismentioned, I don't know. So this is kids, and this is this. Perhaps you can see better from here.
The field ones are, I think,
Sorry, can you repeat?
I think the field contours are the original, and then the empty ones are the
What we do, yes.
The last function has been changed.
Yes.
So they both move up when you do.
That's what we want, yes. But at the price that you have to change that log your mass function. Which is is something that you can do because you have uncertainties on these parameters. But because they are both simulation dependent.
Okay, thank you, Francesco.
Thanks.